Welcome to this lecture. So as before, let's quickly recall what we have done so far. So in this week, we are looking at measures which allows us to look at how likely certain events are in some random experiment, or how large or important a set is in a general measurable space. We had looked at the probability measures which associates to the whole set the total mass 1, and therefore all the other subsets will have mass less than 1. So we are looking at such measures in the last lecture, and then we had obtained certain nice properties of probability measures, and in particular we looked at certain explicit ways of constructing probability measures, like using convex combinations of known probability measures. Now, with those examples at hand, this is the right time to look at the properties of measures or these set functions. Some of the results that we are going to discuss will be specifically for probability measures, but otherwise this will be for general measures. Let us start and go through the slides. Okay. So as before, we are starting off with a measure space omega script f mu. So mu is a measure on the measurable space omega script f, and we are going to concentrate on algebraic properties of the measures mu. So what do we mean by algebraic properties? That means we are going to look at certain kind of inequalities which involve addition, subtractions, and maybe multiplications, and so on. So let's look at these inequalities. So just to recall, we already have certain nice properties about measures. So what are these? So let's just quickly go about these facts. Let's first quickly recall these facts about measures. The measure of the empty set is 0. A measure is a non-negative set function, and it's finitely additive and countably additive. The measures of each arbitrary subset in your sigma field is dominated from above by the measure of the whole set. So the measure of the whole set is the maximum value achieved by the measure mu. Then if you add up the measures of A and A complement, you get back the measure of the whole set. So in fact this was proved earlier, and by means of this we proved that measures of arbitrary subsets is dominated from above by measures of the whole set. And finally we defined probability measures as measures with the property that mu of omega is equal to 1. Okay. So with these basic facts about measures at hand, we are now going towards looking at certain algebraic properties of measures. But before that, before we start the discussion, we introduce this terminology. First, we are going to talk about something called finite disjoint unions of sets. So suppose you look at certain collection of subsets which we call as script epsilon. So this is just a collection, arbitrary collection. We say this collection script epsilon is closed under finite disjoint unions if for arbitrary positive integers n, you look at pairwise disjoint sets a1 to an coming from that collection script T, then their union is again in script T. So again we are not allowing arbitrary subsets a1 to n, we want pairwise disjoint subsets for any arbitrary number n, but then I want their union, this is a finite union, I want their union to be in epsilon. So if this happens for all arbitrary such n and a1 to an, then I will call script epsilon that collection is closed under finite disjoint unions. Similarly, we now define a corresponding concept for countable disjoint unions. So again we look at a collection script epsilon, and then we say it is closed under countable disjoint unions if for a sequence of sets, now the set should be first of all pairwise disjoint, then for those kind of sequences I want their countable union to be back in the collection script epsilon. If it so happens for arbitrary such sequences with pairwise disjoint sets, then I will call that script T is closed under countable disjoint unions. Okay. So with these two operations, we are now ready to discuss certain interesting properties of measures. So earlier we have already recalled some of the basic facts about measures that we have already seen, and now using those properties we now derive certain more interesting properties. Okay. So first property is involving two probability measures. Later on we will see some more properties involving general measures. So let's start with P1 and P2 probability measures on some appropriate measurable space omega f. So they are defined on the same measurable space. Now we look at this collection. So this is defined in a very special form. We want those subsets in your sigma field such that the probability of the sets under P1 and P2 match. So if the probability of the set A has the same probability under these two different way of measuring P1 and P2, then I will put it in the collection script A. So that is the collection. Now what is the claim of the proposition? So we claim that this is a first of all a non-empty collection, and then it is also closed under complementation, and it's also closed under finite disjoint unions and countable disjoint unions. So this is a very special collection of subsets of the original set omega, and we are choosing these subsets from the sigma field, and we are saying that this collection is non-empty and it's closed under these important operations: complementations, finite disjoint unions and countable disjoint unions. So how do you show this? Let's prove them one by one. First, observe that the measure of the whole set is 1 because we are looking at probability measures. So therefore omega, which is of course contained in your sigma field, must be such a set that we have described. So therefore omega is in your script epsilon. So therefore this is non-empty. Great. So let's try to see why this is closed under complementations. So you look at an arbitrary set here, and you want to show that its complement is also in the same collection. So to check that, first observe that as per the definition, the probability of the set A according to P1 and according to P2 must match. But then you now try to compute the probability of the complement. But according to the formula that we have, probability of A complement according to P1 is nothing but 1 minus P1 of A. P1 of omega is nothing but 1. That's the probability measure itself. But then P1 of A is equal to P2 of A. So just write that, and immediately you get that this equality holds, that A complement has the same mass whenever you are looking at under P1 and whenever you are looking at under P2. So no matter which probability measure you use, P1 or P2, you get the same mass for A complement, provided A already has that same property. And hence A complement, which is in your sigma field, must be that in the special collection script epsilon, and therefore script epsilon is closed under complementation. Great. So let's now try to show finite disjoint unions is also such a nice property for such a collection script epsilon. So choose some arbitrary number of sets a1 to an, but finitely many. Suppose they are pairwise disjoint. I want to claim that their union is also in script epsilon. So how do you show this? First of all, since AIs are in your collection, then their probability according to P1 and according to P2 must match. So for all I from 1 to n, this is the equality that you already have. But then you use finite additivity of the individual probability measures P1 and P2. If you use that, then look at the probability under P1 of the union of the sets. That can be split as the finite summation of the probabilities of AI according to P1. But then P1 of AI is equal to P2 of AI, write that, and again use the finite additivity of P2 to get this last expression on your right hand side. And immediately it says that this union AI is also in your collection script epsilon. Therefore script epsilon is closed under finite disjoint unions, and here we have used the finite additivity of the probability measures P1 and P2. The remaining property is about countable disjoint unions. But then the proof goes again in the exactly same way as done for finite disjoint unions. You look at a sequence of sets which are pairwise disjoint, use the facts that P1 and P2 are probability measures and they are countably additive. Using that, you can prove this fact. This part is left as an exercise for you. Please work this out. So therefore, just to consolidate, we have looked at these algebraic operations involving set operations, and we are looking at these special collections for any two arbitrary probability measures defined on the same measurable space, and then this collection of these special subsets turns out to have these nice properties. We will see more properties of this collection later on. Okay, so now we concentrate our attention to general measures. Okay, so suppose you take any two arbitrary subsets in your sigma field, and suppose mu is a measure as taken earlier. Now I claim that this equality holds. What is this? This says measure of A union B and measure of A intersection B. If you add them up, this agrees with measure of A plus measure of B. Okay, so how do you show this? So start with the right hand side. The trick here is to start with the right hand side. So start with the set A and set B and observe that this can be written at pairwise disjoint union of certain other sets. What are these? So I write A as A intersection B and A intersected with B complement. So I write A intersection B as one set and A intersection B complement as another set. But then by the construction, A intersection B and A intersection B complement are pairwise disjoint. Similarly, I split the set B as this pairwise disjoint union of A intersection B and A complement intersection B. Use the finite additivity of mu, you immediately get this relation that measure of A plus measure of B equals mu of A intersection B. So that was one of the terms that is here, but the other three terms I put them together under this bracket. So there is a reason for doing that, but you see that you have measure of A intersection B appearing twice. So we keep one outside and put the other one with the remaining terms within this bracket. Okay, so now you use finite additivity to claim that whatever term is within the bracket is exactly the measure of A union B. Why? Because A union B is the finite disjoint union of the sets A intersection B complement, A intersection B and A complement intersection B. So this is a very standard set theoretic property that A union B can be split as pairwise as the disjoint union of these three sets. Therefore, you apply the finite additivity and combine the sizes of these three sets together to write measure of A union B, and hence the required equality follows. Okay, so let's go back. So for any arbitrary subsets A and B, you get that the measure of A union B added with measure of A intersection B, you get back measure of A plus measure of B. Now as a consequence, you get this corollary that if you take two subsets now A and B, but with this additional property that B is a further subset of A actually, then what happens? Then that earlier relation reduces to this relation. How? A, you can write it as the pairwise disjoint union of B and A minus B. So that is one way to go about this. Another way is to simply apply previous proposition and simplify it to this one. Okay, so there are two ways of proving this equality. So one here, since A is a bigger set than B, you first write A as a disjoint union of B and A minus B. So write using finite additivity. Another option is to use the previous proposition. But then from this equality, there is a very interesting relation that follows. Since mu or size of A minus B, that set, is non-negative, since mu associates non-negative values, mu of A minus B, that is non-negative, you get that mu of B is less or equals to mu of A. So this is a positive non-negative quantity and hence you get this inequality. Okay, so here as long as B is a subset of A, measure of B cannot be more than measure of A. So that's an interesting property, some kind of a monotonicity relation, algebraic relation for the measure mu. So try to work them out, write them out, but I have already discussed the main ideas for the proofs. But given a sequence A1, A2, AN, recall that earlier we had discussed an interesting construction in exercise 12. This was in week 1. So let's recall what we had done. So given a sequence of sets or maybe a finite number of sets A1, A2, AN, you can construct certain sets B1, B2 and so on. such that these properties holds, that the unions of ANs is matching with unions of BNs, BNs are subsets of AN, but further the BN should be pairwise disjoint. So you can construct sets B1, B2 and so on, which are pairwise disjoint, which are subsets of original sets AN, but their union matches with the unions of AN. Okay, and notice that the union of BNs is nothing but a countable disjoint union now, because BNs are pairwise disjoint. So this is something we are going to use from now on. Just to recall about this exercise 12 that we are talking about, this was actually for any finite number of sets A1, A2, AN. But if you fix the first n elements, first n sets A1, A2, AN, and construct these sets B1, B2, Bn, then you exactly get this property. So here you vary for any n, then you can construct the corresponding Bn by the same construction method. Okay, so that is the idea, that it was earlier explained for finite number of sets A1, A2, AN, but then you can repeat for any n and obtain the Bn and prove these three properties. So this is easy to observe, but then we are going to use this specific type of Bn's in our later results. So this is immediately going to be used in proposition 8. Alright. So remember, for a sequence of sets An which was pairwise disjoint, we have countable additivity of the measure mu, which said that the measure of the countable union is obtained as the sum of the individual sizes. So that was what we called as countable additivity of a set function of a measure mu. But then what we actually have is that for arbitrary sequences where there may be intersection between the sets, you actually can claim an inequality. You can no more claim equality, but you can claim an inequality. What does it say? It says that the measure of this countable union is at most the series value which is obtained by adding up the individual sizes of the sets. To prove this, we use the sequence Bn as constructed above. What do we do? So take those Bn's. Remember, Bn's are pairwise disjoint. Union of Bn's is same as unions of An, and Bn's are subsets of An. So we use all these properties. First, observe that this countable union of An's is nothing but countable union of Bn. So that you write first. Since Bn's are pairwise disjoint, you have apply the countable additivity of the set function mu, of the measure mu, and you get this summation that you have to add up the individual sizes and you get this series. So that is the countable additivity of the measure mu. But then Bn's are subsets of An's, so therefore measure of Bn cannot be more than measure of An, and hence you get this inequality, this upper bound that is given by adding up the individual sizes of the sets An, and therefore you get this inequality that was stated in the proposition. So therefore, when you are working with pairwise disjoint sequence, you get an equality, but otherwise for general sequences you can at most claim an inequality, and this is the upper bound. Okay. Now this is an interesting comment. So this is about the discussions in proposition 7. Remember, we proved that for any measure of A union B together with measure of A intersection B, if you add them up, that will be exactly measure of A plus measure of B. But then you would like to transfer the measure of A intersection B to the other side, and thereby you would like to write measure of A union B in terms of these three things: measure of A plus measure of B minus measure of A intersection B. But you have to be careful here. If it so happens that you are dealing with an infinite measure, then measure of A intersection B may be infinity. If you are dealing with an infinite measure, then measure of A intersection B may be infinity. In that case, you have to be careful when you are subtracting. So remember, infinity minus infinity is not defined. So if you want to subtract this infinite term, measure of A intersection B, if it is infinite, then you are not allowed to do so. You cannot define infinity minus infinity, so therefore you cannot cancel off the measure of A intersection B that was earlier on the left hand side. So you cannot subtract it and put it on the right hand side. Okay, so you can do it for finite measures, or if you are given the information that measure of A intersection B is finite. only then you are allowed to write this formula that measure of A union B is measure of A plus measure of B minus measure of A intersection B. But this is true for any finite measure, so you don't have to worry about that. And in particular, this is of course true for probability measures. And that gives you back your familiar formula that probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B. So that is your familiar formula that is now generalized to arbitrary finite measures, for example. Now, by the principle of mathematical induction, you can now extend it to n many sets. So you can extend it to finitely many sets and you get the result which is called the inclusion exclusion formula. So here you are considering n many sets now. So here I am taking a finite measure once more just for the sake of well definedness. We don't want to subtract any term which is infinite. So just for simplicity, let's work with finite measures. Then we are saying that if you choose n many sets a1 to an, arbitrary n many sets, then the measure of their union, this is a finite union, can be written in terms of an algebraic expression like this. So it's a addition and subtraction of certain terms. What you observe is this. So first you add up the size of the individual sets according to the measure mu, but look at pairwise intersections and subtract out those sizes. Here you should choose I and j so that they do not get repeated. So that's why I have put I less than j. So as I and j varies from 1 to n, you get all possible pairs ai and aj. Okay. So you look at all possible such intersections, pairwise intersections, and look at the size of that, you subtract them out. Then next step, you add the term which is intersections of 3 terms like this, 3 sets like this. So you take ai, aj, ak for example, with ijk distinct, ijk runs from 1 to n, but here you add them. So that's the sign gets flipped. So start with plus sign, then for pairwise intersections you add minus sign and so on. And at the end you will end up with this term which is the intersection of all the sets, and look at the size of that. You associate the sign minus 1 to the power n minus 1. So that is the general formula. So here what you are doing, you are first taking the sets A, then you are subtracting out the common parts, then adding up the triple intersections and so on. This is again a generalization of the results that you know for probability measures, and this is left as exercises for you. This can be proved in many different ways. One of the ways is just by extending it by mathematical induction, by the principle of mathematical induction, using the case for 2 sets. From 2 sets you can go to n sets by principle of mathematical induction. That's one way of doing it. Other way of doing it is by counting the appearance of an arbitrary element in these sets. So basically what you are doing is that if you go via Venn diagram of these sets a1 to an, you are just looking at how many times you are counting these sets. If you have counted the sets ai's once at a time, then you have already counted the intersections twice. So that's why you are subtracting out the pairwise intersections. But if you subtract out the pairwise intersections, what you have already removed are the triple intersections. So that's what you have to add. So that's why this formula comes with plus and minus signs in an alternative sense. So alternatively you get plus or minus signs and you get this expression which is known as the inclusion exclusion principle. So try to prove this. That again, the hint is you can use the principle of mathematical induction and apply and prove this. Use the principle of mathematical induction and prove this. So this is again left as an exercise. So we have discussed some algebraic properties of measures, and we are going to see certain nice properties involving continuity in the next lecture. So we stop here.